All right, everybody. Welcome to a new season of Discrete Optimization Talks Dots. We have two dots today. The first is by Bissan Ghaddar. She is the John M. Thompson Chair in Engineering Leadership and Innovation and an Associate Professor of Management Science and Sustainability at the Ivey Business School, working on problems at the intersection of machine learning and nonlinear optimization. Before joining Ivey, she worked on energy, water, and transportation network optimization at IBM Research and eh, um, and on inventory management problems at the Center for Operations Research and Analysis at the Department of National Defense Canada. Been published in math programming, IJOC, SciOpt, among other places. Her research has been supported by the NSERC, OCE, Cisco, H2 2020, and Marie Curie International Incoming Fellowship. She serves as the research lead at the Ivey Energy Policy and Management Center and is a fellow of the Balsillie School of International Affairs, engaged in the research cluster in AI, Global International Public Policy. She is the associate editor of she's an associate editor for the Euro Journal on Computational Optimization, and we're very happy to have her for the first dot of the season.
Thank you so much, Alexander, and thank you for Sylvia and yourself and Elias for the nice seminar series and for having me speak here today. As you mentioned, I'll be talking today about learning for nonlinear optimization. And this is a joint work with my collaborators at the University of Santiago de Compostela in Spain. So before starting to talk about the learning for nonlinear optimization, I want to focus on polynomial optimization problems, which will be the main type of problems that we will be doing the learning for. So these types of problems are interesting from a theoretical point of view as well as from a practical application point of view. So they have the following form where you're trying to minimize or maximize a polynomial objective function of a given degree, and you have a set of polynomial inequalities and equalities. In our case, we also assume that x, the variable x, is bounded by an upper bound and a lower bound for purposes that I'll talk about later on. Now, these problems have really nice applications in energy, gas, and water networks, as I will be talking about next. So in particular, in my area of research, I focus on polynomial optimization for water and energy networks. And these networks really have a commonality in terms of the structure as well as the formulation of the problem. So for example, for water networks, we have the placement of pressure reducing valves, and we have on the operational side, pressure setting type of problems. On the energy network side, we have transmission expansion planning for the design problems, and we have optimal power flow, which is a really famous problem in this area. And these all problems, like our polynomial optimization problem, they are mostly quadratic problems. They have also a commonality in terms of the constraints. For the water networks, you have the water friction loss, which can be modeled as a non-convex quadratic constraint. For the energy side, we have the power flow losses, and we have other types of constraints related to the physical aspect of the network. They also both exhibit structure, and this is really important when working with polynomial optimization, because then that can be exploited and lead to more computational efficient solutions. So this is the motivation why we're interested in polynomial optimization and solving these problems. So again, we have the following formulation. So these problems typically take the following form. What we will be doing today, and for the purpose of today's talk, I'll be focusing only on RLT type of relaxations. In general, we also use conic type of relaxation like SDP, semi-definite programming, or second-order cone programming. For today, we will be focusing on RLT, but the work that I'll be talking about here can be extended to any type of other relaxations. So for the RLT relaxation, what we will be looking into is the following. So we have, again, the set of the objective function and the set of constraints. You have monomials xi times xj, for example, or xi times xj times xk. We will be defining the RLT variable along this j set as follows, which is the product of monomials related to the variable x. Okay, and then we also have bound factor inequalities. Because you have xj to be bounded between upper bound and a lower bound, this can also lead to bound factor constraints. These will be redundant to this formulation. However, when we take the relaxation, this will be really important when we take a look at RLT relaxations. So because we have x to be non-negative, xj minus lj to be non-negative, and uj minus xj non-negative, so any products of these types of constraints will also lead to non-negative inequalities. So what we have here, so we have the same formulation. We will add these bound factor constraints. We will linearize all of these constraints. And how do we linearize them is we will just replace the monomials with their corresponding RLT variables. So for example, if you have x1 times x2 monomial, you will just replace that by x12, and that will lead to a linear form of this monomial, and so on and so forth. So you'll do that for all possible monomials appearing in the polynomial optimization problem. Now you can have also the RLT identities to make this problem equivalent to the original problem. However, when we solve the relaxation, we will remove this part, and this will not be present, and we will end up with a relaxation. So to be able to get back to the optimal solution of the original problem, we have to do some sort of a branch and bound algorithm, and we'll be using spatial branching to be able to finally get to the solution of the original problem. So now in terms of branching, and that's the main thing that I'll be focusing on. So we can branch on different things, and the way that you select this branching will impact a lot the computational efficiency of solving this polynomial optimization problem. There are different ways in terms of branching for this type of RLT relaxations, and I'll be talking about them next. So one way is for each variable xj, you will have this theta j that corresponds to the violation of x bar j union j minus the product of xj and xj. Now, this is the maximum violation across all possible monomials that interact with the variable xj. Another option is to take the summation of this violation, of the absolute value, sorry, of the violation. And a third option is to take the weighted sum. And the weight can be different things, and I'll talk about it in a bit. So there are different ways to branch, and to select this variable j that you will branch on, it will have the maximum violation, okay? So it will have the worst in terms of, or the highest value in terms of theta j. So now if you want to consider or focus on wj, or the weight, we can consider it to be just the sum. If the weights are all 1, this is exactly equals to the sum which I talked about before. We can have the dual, what we call like dual branching criteria. And this wj is going to be the absolute values, or the sum of the absolute values of the dual values associated with the constraints that contains the monomial j union j. Okay, so wherever you have a constraint related to this monomial, you will have the dual value, and you take the sum of these absolute values. Or the range. The range corresponds to the ratio between the range of the variable at the current node of the branch and bound tree compared or divided by the range at the original root node. So it means like how far did this variable go in terms of the range? Did it, if it's 1, this means that the range didn't change, or the upper bound and the lower bound of this variable stayed the same until that node. If it's less than 1, then it's shrinking, and the lower that value is, it means that it's really bounded by a very small interval. So this gives us like 4 options, like the max, the sum, and the dual, and the range. And which one to choose, it's still a bit tricky. Like we can have some problems where one is better than the other. We additionally, on top of these criteria, introduced 2 additional criteria related to the following. So we represent the polynomial optimization problem by a graph, and we have 2 types of graphs that we will be considering. The variable intersection graph, which means that for each polynomial optimization problem, you have the set of variables. So let's say you have n variables. So you create a graph with n nodes, and each 2 nodes will be connected if that monomial or the product of these 2 variables appear in the polynomial optimization problem. Okay, and then we have the constraint monomial intersection graph, which is a bipartite graph. We have the nodes corresponding to the constraints and the nodes that correspond to the monomials, and these would be linked with each other only if that monomial appears in that corresponding constraint. And now that we have these 2 graphs that we will be looking into for polynomial optimization, we have certain graph measures that are interesting. And for the purposes of branching, this eigenvalue centrality is going to be important. And what I mean by eigenvalue centrality is for each variable j, we can compute this eigenvalue centrality or eigencentrality for the Vig graph and for the CMIG graph. And this shows how connected is this variable to other nodes, but not just to how many nodes it's connected, but to how many other important nodes. Okay, and that's can be computed from, like, you can take the adjacency matrix of this graph, and you can compute the eigen vector, and then you can find the eigencentrality for these variables. There are other graph measures that we will consider, but these will come later on. They are not related to the branching explicitly, but this will come later on. I'll talk about them later. But the eigencentrality will allow us now to have two additional branching criteria, and these weights will be either the eigencentrality in the variable intersection graph or the eigencentrality in the constraint monomial graph. Okay. So now we have 6 branching criteria that we are able to choose from. And for all of these criteria, we still have convergence. So we have a convergence to global optimality under this following theorem. Now that we have like the branching rules that we can select from, we want to see or to understand how can we like test the performance of these branching rules. How can we say one is better than the other? Okay, so we will define what we call as the pace. And this pace, it's the time it takes to increase the lower bound by 1. So it's the time, the computation time, divided by the lower bound at the end of the branch and bound tree minus the lower bound, what it was at the root node. Okay, and because we have like a lot of portfolio of branching criteria, we'll be normalizing that. So we'll be dividing the space by the lowest pace, and then we end up with a normalized pace that is between 0 and 1. And the value that is closest to 1 means that it's the best. Okay, so these branching rules, like if a certain branching rule performs with a normalized space very close to 1, it means it's performing very well in that sense. Why did we take this formula of the pace? Why didn't we just consider computational time or gap, which is considered in most cases? The reason is because for our data sets, like we have both. We have problems that are solved within the time limit, but we also have problems that will not be solved within the time limit. For the problems that are solved within the time limit, you can consider just the time, the computational time, and compare that and say, okay, this is better than this. But then for the ones unsolved, they will all finish within the time limit, let's say 1 hour. And then you cannot compare them, or you cannot assess which one is the better than the other. So there you need the gap, okay? And in the solved problem, the gaps will all be 0 or very close to 0, so you cannot use the notion of gap. So you need this combination between time and gap, and that's why we came up with this pace. And I think the pace, or in our case, the pace really gave us a sense of this solved problems, which one is better than the other, but also at the same time, the unsolved problems, which criteria was better than the others. So it had all of these linked together. So now that we have like the criteria, or how we'll be assessing these branching criteria in terms of performance, we would like now to see the features for each of the instances that we have. What features would make sense to include in our problem or in our learning algorithm? Okay. And for our learning, we tried like 3 different things. Again, I would like to here mention that these are really basic learning algorithms. We didn't do any sophisticated type of learning. The reason is because for mixed integer programming or mixed integer linear programming, a lot has been done in terms of learning for the branching and the branching selection. But for nonlinear optimization, not much has been done. And we wanted to start with something really basic to see how far we can go. And for our purposes, we used the quantile generalized additive models and the stochastic gradient boosting. And then finally, we also checked tried the quantile regression forest. So all of these 3 approaches were tried on our test instances. Now, to feed these instances or to extract from these instances certain features that will allow us to learn, we tried various things. And then we finally have a list of these features that, 34, I believe, features that made sense for our approach. And these can be divided as follows. So there are features related just to the variables of the instance, to the constraints, to the monomials, to the coefficients of the monomials, and also some other type of features, for example, related to the degree and the density of the polynomial optimization, related to the number of variables of the RLT variables, and finally, graph-related type of features, which I talked about at the beginning. And because we have now this variable intersection graph and constraint monomial intersection graph, we can now use the density of these 2 graphs, the modularity, and the tree width and retransitivity. And these are additional features that we will be including in our problem. So we have these sets of features. We have our test instances that we have taken from the literature. So there's the differential test instances that are randomly generated, and the degree there varies between 2 and 7. And we have different densities of these problems. We have the MINLPLib, and this is based on real problems. And then we have the quadratic QPLIB. Okay, so these are in terms of our test instances. And in terms of our implementation, we have our own solver, and this is done by the University of Compostela and University of Santiago de Compostela. And we have the Raposa solver, which is the global optimization solver for polynomial optimization, and it's based on RLT. So what we have is now we have the features, and these features, I just want to mention that are static. So at the beginning, we have an test instance. So we will get a test instance. We have all the features extracted. And then based on that, we will, based on the learning, we'll say, okay, which of the selection for the variables is the best approach. And then for the branch and bound tree, we'll be using all of this criteria that we just found throughout the branch and bound tree. And for the learning, as I said, the output, that most important output that we have, or like that we will be assessing the performance, is the pace. Just before we start the learning, I just want you to understand or to take a look at the portfolio of instances that we have. And is there actually a purpose of learning? Like, can learning be done? And what we did is we applied all of the 6 criteria on all of these test instances, and we checked which one was the best for a given instance. Okay, so for the DS instance, you can see that, for example, the range had most of the problems, like it was best on most of the problems, and then the second best was the dual. For the MINLP as well, similar type of thing, but for the QPLIB, you can see that the range was performing not very good, and the one that would perform the best was the eigencentrality CMI. Okay, so there's actually a richness in terms of the portfolio. It's not clear if you take any random instance from this data set, it's not clear which branching criteria would make sense to apply. And as you see here, for example, the eigencentrality CMI is good on the QPLIB, but not on the DS and the MINLP. So if you use it for each of and every instance on the MINLP, you will not get a good performance. And this is another way to seeing this diversity in terms of the portfolio and then choice of branching criteria. Again, you can see the same thing here. Like the range is very bad on the QPLIB because the pace ranged like from the very small value up to 1, while in the DS instance, it was very close to 1. And also similarly here, the eigencentrality CMI was very bad on the MINLPLib, for example, while it was very good on the QPLib. So it's really important what choice of branching criteria you want to use. And if you choose the best rule, actually, which is the range across all of them, on average, the range was the best across all of them. If you choose that criteria for each and every one, you get a geometric mean of the pace, a value of 1.87. While if you pick the optimal rule, so for each instance, you check which one was the best and you pick that, the geometric mean of the pace was 1.187. So there's actually a room for improvement from the best to the optimal, and that's a 36.7% improvement. So we are trying now through the learning to get to this as close as possible to this number. And can we do that? We have some improvement. It's not exactly the optimal, but we were able to get an improvement up to 24.5%. So from the best branching rule, which was 1.87, we were able to push that to 1.4. And that's really a good improvement, going from like the best to 24.5% on top of the best. And that was done through the learning through the regression forest. So sorry, through the random forest. So if we apply the machine learning approach and we apply it on all of the test instances, you can see this is the red one here is the MLQRF. You can see that the pace is very close to 1, or the normalized pace is very close to 1. Similarly in the DS and similarly in the MILP as well as the QPLib. compared to all of the other approaches where you have a bigger range in terms of the performance. So that shows that also the improvement or the machine learning is able to get a good improvement for these test instances compared to the other branching criteria. And if you compare it to the optimal branching criteria, you can see that it's more or less mimicking the same behavior, especially, for example, in the QPLIB and the MINLP, and also here with some differences, like in terms of the Ike CMI. So you can see for the MINLP and the QPLIB, it's exactly the similar proportions of the branching criteria were selected in the optimal and in the machine learning type of approach. One thing we were also able to see is what features were important for the learning. And because we're using the random forest type of approach, we were able to extract the feature importance. And in this case, you can see that the graph extracted features that we proposed have a big impact on the learning. So for example, the modularity, which is the first one. Also here, the VIG modularity. So on the two graphs, the CMI and the VIG, it had a big improvement or a big performance impact on performance. Also the density as well here as the density. And all of these other features that were important in terms of the variables and the coefficients and the monomials and so on. And this is like the top 15 features, I believe, that we were able to extract that were really impactful on our learning. Now, can we do more? So this is one approach that we proposed in terms of selecting which branching criteria would make sense to branch on for a given nonlinear optimization problem. Can we do something additional on top of that? We applied a similar type of learning approach, but now instead of selecting the variable to branch on, is selecting which type of cuts are really important or are really powerful for a given instance. And there we experimented with 10 different types of cuts. We used the basic RLT relaxation, and then we used linear SDP cuts. We used second order cone programming type of cuts, first in Gurubi and then in MOSEC as well. And then we also used SDP type of cuts, again, SDP type 1 and type 2. I don't want to go into the technical details, they are in the paper, but we use a variety of 10 different cuts on the same set of test instances. And we tried to learn, are there certain cuts that are better than others for a given test instance? And you can see the pace. Again, we use the normalized pace. And the machine learning approach had a really much better performing results compared to the others. The others are really like performing all over the place. Some cuts are really good for some instances, but some other cuts are really bad. And you can see here in the performance profile picture, like the red one is the machine learning, and the rest are related to the 10 different type of cuts. And for certain instances, for example, we were able to show that the SOCP and the SDP conic constraints or the conic cuts that were added were really good for high density problems. So density also played a role in that sense. And also for the water-related problems in the MINLPLib, the SDP constraints perform the best. So there are certain structures in the problem that would make sense for certain cuts to be added versus others. And there we had a 32% type of improvement compared to the standard RLT type of relaxation. So there was a really room for improvement while using the learning. And an additional step that we were also able to do is to use the cuts and the branching selection with each other. So this combination of selecting the cuts and selecting the branching and combining them together in a learning approach. I don't show you the results here, but they are also in the paper where we have even a better improvement than this 32. We were able to reach up to 48% in terms of improvement. Okay. And what we are now currently doing is instead of like the static learning where you're just learning from the features of the static problem at the beginning and using everything throughout the branch and bound tree, trying to do a more dynamic type of learning where at each node of the tree, you're trying to either select which branching criteria would make sense at each node instead of selecting one criteria that will go throughout the tree. So that's I would say, a higher level of complexity because there's a lot of features to be included. The problem becomes very hard to learn because you have thousands of nodes that you're learning from. So it's a different level of complexity, and we're still in the first phases of working into that. For the rest, whatever I talked about today, they are like combined in 3 different papers. You can see them on this. The first one was published already in Informed Journal on Computing. The other 2 are under revision and they are on archive. So if you're interested, they have more details in these papers about the learning for conic constraints and the learning for branching selection. And I think I'm right on time, so I want to just conclude with an announcement. We have a special issue in the Euro Journal on Computational Optimization. It exactly fits into the topic of machine learning and optimization. So if you have any research or work related to this, whether on the application side or on the theoretical side, we'll be very happy to receive your contribution. And if you have questions, you can reach out either to me or to Marcus, who's the other guest editor. And the submission deadline is end of this year. And thank you so much for listening. And I'll be happy to take questions either now or also at the end during the breakout sessions. Thank you.
Thank you so much. We actually do have a couple of minutes, maybe 3 minutes for questions. If anybody has a question, you could either write it in the chat, or if you raise your hand, I can unmute you. Actually, it's possible you're able to unmute yourselves. Yes, Imre.
Yeah, so thank you for the talk. I have one question about the computational aspects. Is there any validation runs done, or is the tuning done on the entire QPLIB and MINLPLib set? Is there anything held back and then?
Yes, yeah, we do a training and testing. Yes, yeah, we have a training and a testing, yeah. And because we have like the random first, we do the OBB, like OBB, out of bag.
And actually, well, let me wait to see if anybody else has a question. If not, then I have a quick one. So I saw that in most of the results, basically 1 or 2 methods would be enough to get. Would it be easier for the training if you just restricted to the range and the eigenvalue method?
No, we tried that. No, because there's actually other like so if you see the portfolio, it's really rich like here. So there are like really big parts also where the dual is really performing very well on certain instances. Like you can see here, it's around 25% for the DS and similar to here. Also the max and the MINLP that's performing very well on certain instances. So I don't think if you limit it to 1 or 2, even like I think 6 is still like maybe there are more that can be explored and can be investigated to get a better type of outcome. So we tried to restrict it, but no, the performance of having this rich portfolio made sense for us and made sense also for the learning. So there was instances where the max was selected, the sum. So we didn't find any from the learning, then none of these were selected to be.
Sure. I guess my thought was like you had this improvement of the optimal among all 6, but then you could do like optimal among 1, optimal among 2. Like there's an increasing level of complexity by adding more, but I would imagine there's like a diminishing returns by adding more options. And so the trade-off being that maybe the training is easier, maybe with a best of 2 instead of a best of 6. That was my only thought.
Yeah, like in terms of the training, because it's like there's no overhead, right? Like it's not done once. And that's like in terms of the computational overhead, we didn't have that much. And that's why also it made sense for us to use all 6. And we have results in the paper where it shows like where it ranked, for example, in terms of the ranking, where did each approach rank compared to the others. And that's why we thought, okay, there are like a lot of variation. So it's was worth it for the improvement to achieve this 24% or around 24%. It was important to use all of them.
Thank you.
And for the when we combined it with a selection of cuts, we didn't use all 6. We restricted to I believe 3 of these, and there because we started having like 3 times like 10. So there we tried to restrict it, but in this case, because we had some flexibility, we decided to use all of them.
Thank you. So I think that we're perfectly on time. Let's thank Bissan one more time. And I'll stop the recording here.